to get us started, since it's a few minutes after 4, I think we better get started because I know Dr. Ryan Baumbach quite well, and I know a little bit about his research, and we've got a lot to cover. So welcome to this session, this scientist speed session. As I mentioned, if you have questions for our scientists today, put them in the chat and we'll get them answered. And just thank you for joining us at another MagLab virtual open house session. This is our last scientist speed session. There's one more open house session tomorrow where we'll be covering some STEM camp options. It's a little bit more of a local open house session, right? So we'll be focused on the Big Bend area, the Tallahassee community where the MagLab is headquartered. But if you're interested in learning about STEM summer camp options, we'll be covering that tomorrow at 11, okay? So without further ado, let's give it to our scientists to take over the session.
Okay, well, thanks, Kristen and Carlos. I've been looking forward to this. It's always fun to talk with people, even if it is over Zoom. And hopefully some of you will be able to come in person next year because that's really a lot of fun. We do a lot of demos and okay, well, in any case, what I'm going to do here is start off by telling you a little bit about my background. I'll tell you a little bit about what motivates the type of work that we do in my group. I have kind of a cute video that tries to say a little bit about what our approach is. I'll tell you a little bit. My group especially is focused on synthesizing crystalline materials. So I want to tell you a little bit about that, how that works. And then I will answer any questions you might have, and anything really. And I suppose that if you have questions as I'm going here, and if Kristen or Carlos can get my attention, I can pause at any point. It doesn't matter. Okay, so to start with, my name is Ryan. I'm a research faculty member here at the MagLab and a research professor at Florida State University. I'm from California originally. I grew up close to Sacramento. I was an undergraduate at the University of California in Santa Cruz. And if you're in California, you know that they're the banana slugs, so go banana slugs. That's the best. And then I did my PhD at University of California in San Diego. And then I don't know if people in the audience know this, but it's very, very typical for researchers to do something additional after a PhD called a postdoctoral research position, which is basically 2 more years of hard work. and then you do it again. And then you might be ready to move on to a faculty position. So that's basically my background. I was a postdoc at UC San Diego, which was great. And then I went on to Los Alamos National Laboratory, which is in New Mexico. And if people are interested to know about Los Alamos National Laboratory because of its really interesting history or whatever, I'll be happy to talk about that. It's no problem. Okay, so I am in the area of condensed matter physics, and I want to start by telling you a story that in a way you probably already know the answer or you already know about in some way. And that is that the way that our lives are now as compared to 100 years ago is really fundamentally different. And the reason for that is because of the power grid, right? We have tremendous energy resources that really influences every aspect of our lives. And can't remember if I say this explicitly later on, but I do want to say that the reason that we have something like a power grid is because of something that happened about 100 years ago, 150 years ago. And that was that there was a new understanding of the atom that was developed, right? Condensed matter physics was sort of born in its present form, well, not present form, but the beginning of what we have now, about 100 years ago. So we began to understand the atom, we began to understand electrons, magnetism, and this is what people like to call the first quantum revolution. And it's a direct line from that to this thing that we have now, which is the power grid and our sort of modern lives that we get to enjoy. But of course, there's some really substantial challenges that go along with this. And one of them is that to have a power grid, we also have to consume energy. And I think, this is just a graphic that sort of summarizes where we're getting our energy from. A lot of it comes from resources like natural gas and petroleum, but there's other sources too. And some of these are especially important in the present times from the viewpoint of condensed matter physics, because we want to look at things, for example, like renewable energy or even nuclear energy, and think about how we can grow those slices of the pie. That's a motivating factor in our work. Now, I have to think about the numbers a little bit because they're a little bit hard to grasp for me, maybe for you too. In 2019, the total primary energy consumption per person in the US was 305 million BTUs. A BTU is a British thermal unit. I have no idea what that means, but it's what engineers talk about. But I think to put it in some context, let's think about some things that we actually know about. So to cool a 400 square foot space using AC, like a dorm room maybe, you're using about 10,000 BTUs per hour, okay? Or since we're in Florida and we are having hurricanes and power's going out, and some people have generators, well, a typical generator running under full load is consuming about 10,000 BTUs per horsepower per hour. So that at least lets you start to get an idea of how much energy we're each using, every year. It's a real serious issue. We need it. Not only that, but there's actually growing demand. So by 2030 in the US, demand is supposed to be up by 50%. And what this really means is that breakthroughs are really urgently needed to secure energy resources for the future. It's great that we have the energy resources that we have today, but looking to the future, it's probably not enough. And the ones that we do have all have disadvantages. For example, things like petroleum and natural gas, the energy production sites are really distant from the user. So actually, bringing the power from the power plant to your house wastes a whole bunch of energy. It's something like half of the energy gets lost on the way. I mean, that's not great. On the other hand, renewables have their own challenges. Solar, for example, it really only works during the day. So we need batteries. We need better batteries. And that's a serious condensed matter physics challenge. Also on the positive side, if we have new generation capabilities, this can also generate new use modes. Imagine if you could have something that you wore on your shirt that converted your motion into electricity that could charge your phone. That would be great. So there's potential, lots of potential. So it's not all negative, there's a lot of positive. And okay, so what's the point of basic science? The point is that we want to help to grow the size of the pie, right? Make these slices bigger, and then potentially even create new slices for us to enjoy, right? So that's the bottom line with condensed matter physics. I mean, of course, we care about the beauty of science and nature and but we're also going to use it to benefit society. That's the point. So this is why we're studying condensed matter systems. And I've given you one example, but actually it turns out that there's so many other problems that are of similar magnitude. And I've made a list here. They range from things like quantum computing, which is supposed to be revolutionary for code breaking and I don't know, the banking sector and all sorts of things, all the way over to flexible electronics. Wouldn't it be nice to, if your cell phone could roll up and go in your pocket? Or what if your wallpaper could be a television screen, or all these sorts of things. So there's many problems that are of very large magnitude that can be addressed by condensed matter physics. They're all connected to basic science, of course, but they're also connected to the economy, national security, and all these topics are connected to each other too. So that's, in a nutshell, what we're trying to do, is to meet these new challenges, and of course there's many more challenges to come. That all sounds nice, that sounds like something that's fun to do. But remember, I mentioned that about 100 years ago, we had a first quantum revolution. And when we did this, we got a new understanding of what atoms do, what electrons do, how does magnetism work. And actually, over the subsequent century, we've gotten a really good understanding of how to actually implement that knowledge. But all of these problems that I just told you about are hard problems. And what we know and use routinely about electrons and atoms and so on aren't really going to satisfy the needs. So what we really need to do is to train electrons to do new tricks, right? Like my friend the dog here. This is who I am when I'm in the lab. I'm this baffled and confused dog trying to find new dog bones. And that's not easy. To put it differently, if human beings knew how to shift paradigms, then they wouldn't be paradigm shifts, right? It would just be doing our regular stuff. So we don't actually know how to do paradigm shifts, but there's a few activities that we can do that sort of improve the chances of that actually happening. And one of them is what we like to do in my group, which is to follow this iterative loop where we make things, we go out in the periodic table and we produce all sorts of different crystalline materials. We have some guidance, an idea of where we're going, but we may not necessarily know where we're going. We'll then measure them using various techniques. Then we'll tune them through chemical substitution or squeezing them or putting in high magnetic fields, see what we see, and then we'll do it all over again. And we just do that over and over and over again. And the key step for the research in my group is this make step. We're really focused on making crystalline materials. And so what I'm going to do now is show you kind of a cute video that we made. Well, it's in progress that summarizes some of the concept of how this is going. So I'm going to stop sharing and then I'm going to restart sharing to attempt to show this video. And Kristen and Carlos, if I start it without volume, wave your hands and I'll try to start it over. Okay, here we go. Share sound. Ta-da. Okay, can you see it? I can't see anyone now. I'm just.
No, it looks great. It looks great. Sorry, Ryan.
Okay, here we go.
Scientists can create new molecules that could change our world. But first, they need to shop for the right ingredients. There are dozens to choose from, each one unique. Some are light. And some are heavy. Some are magnetic. Others, not so much. The scientist thinks about ways different ingredients might work together. She may need more of some atoms than others. And don't forget the active ingredients. Finally, it's time to make a crystal. Shopping for just the right ingredients is just one step in the process of making a new material. For the rest of the story, subscribe to the National MagLab's YouTube channel at youtube.com/NHMFL. You'll be notified of the release of the upcoming summer 2019 science blockbuster, How to Make Stuff to Change the World.
Okay. Were you able to hear it?
Yeah, that was brilliant. That was
Excellent.
really cool.
Okay, so first of all, let me just say that we were very optimistic when we said it would be released in 2019, but it will be released in the near future, and please tune in if you're interested. All right, I'm gonna go back to this talk now. Hopefully we'll get back right on that. Okay, does that look okay?
Looks
Fantastic.
good.
Okay. All right. So the message that I wanted to get across there is that when we're thinking about how to make things or where we're going to go in the periodic table to enable this second quantum revolution, what we really have to think about is broadly, what are the behaviors that are hiding out throughout the entire periodic table? And so what we're interested in as crystal growing condensed matter physicists is basically taking the entire periodic table and putting it together in unique ways. There's some really challenging technical aspects to this, and I want to tell you a little bit about what they are. For one thing, to start on this side, it turns out these sorts of guys are easy to melt, so that's good. It means you can get them to do chemical reactions. But actually, they're really tough because they are so air sensitive. If you hold these elements out in air, they'll immediately oxidize. You can go into the middle of the periodic table. There's lots of elements here that I'm sure you know about, like gold and silver and iron. These are not so air sensitive, so you can just hold them on the bench top. But there's a different problem, and that is that they're really hard to melt. So you have to have powerful furnaces to actually get these guys to respond to anything that you want them to do. You can go ahead and work over here. We like boron and carbon because it's everywhere, especially carbon, right? We're carbon-based life forms, and so there's plenty of carbon, but there's all sorts of problems in actually using it for anything because it doesn't like to melt or to dissolve into other things. But since it's so abundant, it would be awfully nice if we could use it for everything. All right, what else? Well, these are p-block elements. They're pretty abundant, but they have some pretty substantial problems. They're poisonous and they like to turn into a vapor really easily. So that's tough. Some more that are easy to melt, but some are poison. Other ones that I want to point out are really important for our everyday lives are these F-block elements that are at the bottom of the periodic table. These are all over the place, like in motors, in the permanent magnets that are in them. They're also in your cell phone, in different types of lighting, advanced lighting that we have in houses, and so on and so forth. So they're pretty critical to our everyday life. And then, of course, sometimes we like to go even deeper into the periodic table and study these more dangerous sorts of things that are called actinides. Okay, so bottom line is that we want to use the whole periodic table, but in order to do this, we need to be thinking about all of these different personalities that elements have. And so we really need a large toolbox of synthesis techniques. And this is the thing that I myself spend most of my time doing, is figuring out how to get these different elements to play nicely with each other. Okay, so now I'm coming.
Hey, Ryan,
Sure.
Ryan, can I ask you a question while you're on this
Definitely.
really great description of these periodic table and all these elements and families of elements? Do you have like a favorite element, right? The periodic table's full of elements. Do you have you have a favorite?
I have so many favorite elements, but let me tell you something that I think is especially neat. If you look down at these guys that are circled in yellow, those are called the actinide elements. And somewhere around uranium or neptunium, even plutonium, that's the end of where elements are naturally occurring. And as you go beyond this, to americium, curium, berkelium, californium, those can only be made synthetically under high energy conditions in things like nuclear reactors. So they're incredibly rare. They're incredibly short-lived. Not many people have ever had the opportunity to study things like that. But in the last decades, there has been a small amount of research in them that is just because they're so difficult to work with and rare. And at the MagLab and at Florida State University, we're one of the few places in the world that can actually do work on those types of elements. So they have a special place in my heart. Is that a good answer, Kristen?
Yeah, it's a great answer, but kind of along those lines, right? This is an Ask Me Anything section. So there is a great question that if you discovered an element, what would you name it?
What would I name it? Oh man.
Or wouldn't it be
would be-
Baumbachium?
No way. I'd name it Tallahasseeum.
Oh,
Love it. Love it.
Wouldn't that be great? That would be incredible. Yeah. So by the way, anyone that wants to discover elements, there's an active research community that works on that in nuclear physics. And the way that they do it is they may be at a place like a nuclear reactor. And what they'll do is they'll take some of these really heavy elements, ones that already have a huge nucleus, and then they'll fire neutrons at it and try to get them to stick to it, basically. Or they'll take two heavy nuclei and accelerate them towards each other with high energy and try to get them to fuse for short periods of time. And so that's the work that has actually led to these guys out here like fermium, mendelevium, nobelium, and well, even you go up in here, there's many more, rutherfordium, So there's a community of people that works intensively on that exact sort of thing.
so Ryan, is this a part of the job that makes you feel like a mad scientist? Because the question was asked, what is the part of your job that makes you feel like a mad scientist?
Yeah, I'd say so. That's definitely a part that makes me feel like a mad scientist. I also this is another neat thing. So probably most people have learned in school that the periodic table is sort of arranged in this way, and these elements are, they are what they are. It's sort of static. Nothing is changing. But nothing could be further from the truth. It's really true that each one has its own personality, but when you combine them with each other, the resulting material will have something that is completely different, or can have something that is completely different. And so a good example is that there are certain combinations of elements. I can't remember off the top of my head the example I want, but like zirconium and tellurium maybe is what it is. I wish I could remember, sorry. In any case, two elements that are totally non-magnetic, right? And you can take these two and react them to form a new crystalline lattice. And it turns out that the new crystalline lattice, even though it's made out of two non-magnetic materials, is now a magnet. And so there's a kind of a element to this that is almost like alchemy, right? Where you're taking things that have their own individual properties, and then you put them together, and all of a sudden you have some sort of emergent new behavior that you wouldn't have supposed would be there.
We did have another question asking about, first of all, when we asked about the periodic, your favorite element, a number of people typed in their favorites. So cesium, tungsten, I'm partial to tungsten. So two questions. One is, what's your favorite synthesis method?
Oh, well, let me go to the next slides and I will show you some of my favorite synthesis methods. I actually have some cool videos that go along with that. Is that all right?
Of course, by all means, you lead, we'll follow.
Okay, so let me say that in order to get probably most elements to react with each other, you need to add energy to the system, right? You need to heat up the system somehow. Sometimes this means heating it up a little bit. I don't know if people have made sugar crystals in their kitchen, but in that case, you dissolve some sugar into water while you're boiling it, and then you let it slowly cool down and crystals will form. But in many cases, you need to go to much higher temperatures because a lot of elements have high melting temperatures. So in order to do this, we make use of many different types of furnaces. The most common type are basically glorified toasters, okay? Someone that's in pottery or does pottery will call these kiln furnaces. But what they all amount to are cases where you have an enclosed space and then you pass an electrical current through some sort of resistor. The resistor heats up and then you can heat your sample in that way. And so what I'm showing you here is just a picture of part of my lab where we have lots and lots of resistive furnaces. And what we'll do here is we'll take our elements and we'll put them inside of some container, like in the upper right-hand corner, These are some quartz tubes with aluminum oxide crucibles inside, and they're sealed under vacuum. And the elements we want to react are inside of the alumina. Below it are some metal crucibles like platinum, nickel, and tungsten, right? You can put elements in here, put them in the furnace, heat them up. And then the lower part here is a picture of one of my colleagues taking one of these crucibles out of the furnace while it's still hot in order to quench it from this high temperature down to room temperature. Okay, so in this context, we do a lot of things. Some methods are listed here, like we may take some elements, just put them next to each other and heat them up and let them react. Something that's a little more sophisticated is something called molten metal flux growth. And this is a partial answer to the question. This is really one of my very favorite methods because this is almost identical to what you're doing when you grow sugar crystals. The only difference here is that, for sugar crystals, your flux is water and it's a liquid at room temperature. For these sorts of things, or the things that we do in our lab, our flux will be some other material that has a higher melting temperature. So for example, we may use aluminum, like aluminum cans, right? Like soda cans. So that melts at about 650 degrees Celsius, which is easily accessed in these types of resistive furnaces. And then what's really neat is that you can take a whole bunch of aluminum and then take other elements that have a much higher melting temperature, like silicon or tungsten. Tungsten has an incredibly high melting temperature. And then when the aluminum melts, those other elements will dissolve into it, just like sugar dissolves into water, right? So then we heat it way up, and by heating it up to maybe 1,000 degrees C, it gives energy to the system that allows the formation of chemical bonds. And so you may get bonding, in this example, between silicon and tungsten, or silicon and aluminum, or some ternary combination. You don't always know what you're going to get. And then you slowly cool it down. And as you do that, the crystals sort of precipitate out of the flux. It's kind of like when snow forms out of the air. That's reaches a energetically favorable situation where rather than being dissolved into what's around, it's going to form crystalline material that falls out. So molten metal flux growth is a powerful method for discovering new materials, because if you mix a bunch of things together like that and heat them up, then you don't necessarily know what's going to come out of it. So it's sort of letting nature do our job for us. It can make new materials that we wouldn't expect, and then we can go and try to learn about them. Okay, so these are great. They're sort of workhorse types of instruments, but what's even more fun is something called an induction furnace, okay? And so while flux growth and resistive furnaces, I love them because they make my job possible and open a lot of doors, I like induction furnaces because they're just a lot of fun. So the idea here is sort of summarized in this left-hand part, where we have a coil of copper tubing, okay? And that's attached to a power supply. And the power supply is putting a AC electrical current into the copper that is flowing around these coils, but it's oscillating back and forth. Now, probably people remember that if I put a current into a solenoid, it makes a magnetic field that's pointing along the axis of the solenoid. So it's pointing up and down in this picture, okay? And if I make that current oscillate back and forth, it means that the magnetic field is also oscillating back and forth. So up and down and up and down and up and down. And then if I take something metal, which is what this square rectangle is, and put it in there, then the electrons that are in that thing will get moved around by the magnetic field that's going back and forth. And when they move around, they bump into atoms that are in this piece of metal that's hanging in there. And then the piece of metal can heat up to very high temperatures. So it's a great way to heat things. And actually, at home, you may have an induction cooktop. Some people are probably familiar with that. The other thing that's really neat about this is that the magnetic field actually puts a force on the material, and it can allow you to accomplish magnetic levitation. And so let me see if I can get this video to play. So we're going to this middle one where you see this tube going into the induction coil.
Is this the levitation melting demonstration, right?
Yep, it sure is. I love this demo. So what you're seeing in there is a piece of aluminum. It's just a little ingot of aluminum. The electrical current is being applied, so you have a magnetic field inside of the coil that's levitating the aluminum. And now you see the oscillations are slowing down because the inside of that thing actually became liquid. So it's not a rigid object anymore. And in just a moment, you probably don't believe me yet, but it's heating up really fast. I don't know if people know this, but something that's glowing white hot is over 1,000 degrees C. It may be even something like 1,500 degrees C. So in a matter of seconds, not only have we levitated this thing, we've also heated it to a really high temperature. And it's a fairly low energy way to actually do that. So we, in my lab, love doing this for doing focused heating of materials and doing it without having to include a container or a crucible. So does anyone have any questions about this?
That's so cool. I just want to tell everyone, I'm going to put it in the chat. We have another video about levitation melting that we made as part of our open house demonstrations, our video demonstrations. So if you want to kind of see more of that, maybe watch it in slow motion, hear it explained by a different researcher at the MagLab, I'll put that in the chat for you to look into for a later date and time. Ryan, there was a question actually from back a while ago that I kind of want to get back to. Sure. And it's a little bit about like your path to this kind of research.
Oh, sure.
It's a very interesting area of research. So maybe you can tell us about kind of how you got to this place. Yeah. And while you're answering that, think about if you could go back in time and give yourself advice as, I don't know, a college student, a graduate student, what advice would you give yourself, right? Knowing what you know now.
That's a great question. So there's two ways to answer this. This is something that, you know, people like me like to talk about. And I've heard lots of stories from other people about how they came to science. And one story that I hear over and over again is that many people somehow, even when they were very young, really thought they wanted to go into science and do research, and maybe even had a certain area of science that they were really interested in. That's what I hear the most. But that's definitely not what my experience was. I always enjoyed school, but even getting to college, I didn't have a specific topic that I was especially interested in. So I was taking lots of general coursework. And so I took some physics. And it turned out that one of the physics professors at UC Santa Cruz named Bud Bridges, who still works there, he's a great guy, he happened to have an opening in his lab for a researcher. And I was just really extremely fortunate that I was in the right place at the right time. And I asked if I could work with him. And so sure, I got to work in that lab, and it was a very interesting experience because most of the research that was done there actually took place at something called the Stanford Synchrotron Radiation Laboratory, SSRL. And it's a large scale facility that's a lot like the MagLab. And so we would go there and we were users. We would make use of their equipment. We'd bring some samples that we got from someone and we'd measure various things about it. And I think one of the really formative experiences about that was that my very first on-site experiment, we had to set up the whole thing. You know, we had to set up the chiller and the detector and blah, 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 everything. I didn't know what I was doing. So I got the job of setting up the chiller. And, you know, what does a chiller do? It pushes water from one place to another. And I put the flexible hosing on it, you know, on the outlet and the inlet. And I went and turned that thing on, and it blasted the tubes off and flooded the room. Okay. So that was unfortunate. I didn't know what I was doing. But the formative part about it was that no one was mad. You know, it was such a nice environment, welcoming, and they just said, oh, you know, you forgot the hose clamps. Let's show you how to put on the hose clamps. And so it sort of started from there, where it was, you know, it was neat to go to this place. The people who were there were welcoming and, you know, interested in education. And for me, that was really the start of how an interest in science developed. Going on, it turned out that in that position, we were studying materials that other people had made and provided to us for those measurements. And I just developed an interest in how were they making these things? You know, I didn't really understand that at the time. So my PhD, I specifically chose to work in a group where, where we would be making the materials. And now I feel very privileged that I get to do that for other students because, like I said, my group is focused on making these materials. And then we send them out to other groups where many graduate students and undergraduates can make use of them. So it's that's my story. I feel like there might have been a second part to that I forgot to answer.
Ryan, one of the questions asked earlier was about the heavy elements and how long they remain in existence.
Oh boy, yeah. So it depends on which one, very much. So let's go back to here. Okay, so ones that are naturally occurring, like thorium or uranium, they're around for hundreds of thousands of years, even longer. They essentially have an infinite lifetime, even though they are unstable. As you move further going in this direction, it gets reduced down to, you know, tens of thousands of years, thousands of years, hundreds of years. And then eventually, for example, if you get to berkelium, which is something that you can really only get from a nuclear reactor, this guy is only in existence. It has a half-life of about 300 days. So if you get some berkelium for some experiment, you have to do your measurements immediately, because within, within even a few months, already a significant fraction of it has converted itself to other actinide elements that are around. Now, if you push even further to Einsteinium, it's days. And then if you go to these really heavy ones, it's really only seconds or fractions of a second.
Wow, how about that? There's a question in the chat here too about the levitation melting demonstration that you showed. Can specific temperatures be reached using induction melting while maintaining levitation, or is it just really hot?
Yeah, no, certain temperatures can be reached. So the power supply that we're using, we can define the size of the electrical current that's being put into the system. And the strength of that current defines the size of the magnetic field that's getting generated. And then that in turn defines how much energy you're able to dump into the electrons that are in the sample. So if we want a lower temperature, we lower the current. And then in order to keep track of what the temperature actually is, we use an optical device called a pyrometer, which actually measures the intensity of the light that's coming off of the hot object. So we can easily have a dynamic range from 400 degrees C all the way up to 1500 degrees C. And it's really just a matter of controlling that current supply.
All right, I've got a question for you. I want to make sure I say this right. A study was published not too long ago about uranium ditelluride being used for superconductors in quantum computing. How would uranium ditelluride function in a superconductor? How would that be different than typical materials? And that came from a high school student.
Great question. That's a very serious question. Lots of ways to answer it. Let me start by defining a superconductor. Okay, actually, let me go back even a further step. So remember, about 100 years ago, people were figuring out what electrons do in solids. And it's funny because at the time, they really didn't know what should happen with electrons when you cool them down. You know, people sort of conceived of electrons as particles that are shuttling around inside of a material. And there was one idea that sort of said, well, if you cool them down, then maybe they're just going to move less and less. And then eventually, if you get to absolute zero, they'll just stop, right? And if the electrons stop, then you have an insulator. You can't get any electron movement out of it. I mean, we know that's not true now, but that was sort of a thought that was going on. Other people thought that, well, maybe, you know, they'll move more easily because the atoms won't be moving around so much and they won't bounce off of them so much. And that's a little bit closer to the truth, okay? But what they really didn't expect, was superconductivity. And so what happens when something enters a superconducting state, you cool those electrons down, and at some point, when the thermal energy, the fluctuations of the lattice become small enough, there's actually a pairing mechanism between electrons. And let me just say something as an aside here. Electrons have an electric field that comes out of them. And that means that if I have one electron and I try to bring another one right by it, they push away from each other. Like they shouldn't be in the same place. But at very low temperatures, it turns out there is a mechanism that's also an attractive mechanism, and it allows them to form pairs. Those pairs are called Cooper pairs. That's a very unique quantum state of matter that you would not have ever guessed. I don't think anyone would have ever guessed that electrons could do that, if not for these early experiments to cool metals down, right? So what are the properties of a superconductor? So while a regular metal is having a finite resistance, even at very low temperatures, for a superconductor, that resistance is absolutely zero, right? Like it's just perfectly zero. And the reason for that is complicated, but it is because it's a new quantum state of matter that is pairing electrons together in a way that they don't pair in regular metals. The other thing that's important to say about superconductors is that they also don't allow magnetic fields to get inside of them. That's called the Meissner effect. And that's another property of their quantumness. That's a quantum property. All right, so that's the difference between metals and superconductors. Now, it gets more complicated than that, but for something like 50 or 60 years from the discovery of that first superconductor, all of the ones that were studied were of a certain type that are called conventional superconductors. But then around the 70s or 80s, it was realized that there's yet another class of superconductors called unconventional superconductors, where the pairing mechanism is even more mysterious than what happens for the conventional superconductors. We have a theory for conventional superconductors. We basically understand what's going on there. But unconventional superconductors, like uranium tellurium-2, form Cooper pairs through a path that is not well understood. But let's speak broadly about what might be part of that path. It's about getting electrons together into a coherent quantum state. And each one of these electrons has its own personality or properties. It has a wave function. And in some unconventional superconductors, based on what we know about how they actually pair together, you may be able to take these wave functions, which are, I don't know, it's very hard for me to say exactly how this works, but take their personalities or their pieces and then use them as the building blocks of qubits, right? So our normal computers are based on bits. They're ones and zeros. But in qubits, which are these entangled quantum pairs of electrons, the state isn't just 1 or 0, but it's also lots of things in between. And being able to access those things in between is a quantum property And it's somehow, in a way that I honestly don't fully understand, fundamental for creating quantum computing capabilities. So,
and I'm going to put a thing about qubits in the chat, guys. If you're like, what's a qubit? How do qubits work? There's a great interview, a qubit Q&A, if you will, that you can use to help learn more about qubits.
and let me say, just as something that's probably relevant for people who are thinking about getting into science. When I started graduate school, quantum computing and qubits and whatever were not part of the conversation, really. This is a very recent development, like last 10, 15 years, that people really and truly believe is a major vector for research in the future. And something I like to mention is that you can go and look at congressional budget documents, which is not something I advise, but it gives you an idea about like what funding might exist out there in the world. And when they talk about condensed matter physics, they don't say much, but what they do talk about is quantum computing. And so if you're going to be thinking about getting into this type of science, there's a very high likelihood that you would eventually work on things relating to quantum computing. It really seems to be the next frontier.
So maybe if you were time traveling back to when you were a young student, you would give yourself a little heads up about, right? No, I'm just, that would be a little more nefarious. Maybe that would be nefarious.
That would be great advice. Yeah.
Ryan, when I wonder if you had a boat, what would you name a boat?
I don't know. Oh man.
I have some suggestions. No,
okay, yeah. What do you suggest?
Is it periodically something? Is it I don't know. Are you into a pun boat name?
I would try to go something with crystals, but I have no idea. I'm not very good at puns. I'm not very punny. So.
Hey, if you guys have ideas for the name of Ryan's boat, you can send them to us on our social media at National MagLab. Let us know what Ryan should name his boat.
I have even another suggestion. So we build a lot of crystal growth equipment, and we actually name some of it. So if you come up with a really good name for a piece of crystal growth equipment, I promise I will name it that. That would be.
Well, I'm all about 80s music, so I know there's a song, Crystal Clear Persuasion, or that may even be late 70s. That's your crystal related musical connection there.
I love it. Now I'll never forget that.
Love
Thank you.
If you guys have ideas, crystal themed punny names, who knows, you might have named something official for Ryan. Do you have, Ryan, what do you do when you're not kind of growing crystals and when you're not like a scientist at the MagLab? Like what's like a hobby that you have or something?
And not dad duties either. So
I know. Well, that was the first thing that came to mind, is that I'm a dad, so I am spending most of my time doing whatever my kids want to do. But besides that, what I especially enjoy is gardening. And I think that I enjoy gardening for more or less the same reason that I enjoy crystal growth. And that is that I like to see nature do things on its own. I think that's really neat. Yeah.
I love that. I love that as a reason. Ryan, we've asked some other scientists in scientist speed sessions, and so I'm curious, are you a member of any, fandoms, something that you like really geek out over, that there's a whole community? Carlos is representing his Transformer fandom quite strongly today.
I mean, I love science fiction. I don't know if I'm really part of a fandom exactly, but I do love science fiction of almost any type. This is extremely geeky, but I also really enjoy US history. So I like to read all the, old, I don't know, long-winded accounts of what happened in this country over the last 400 years. So that's not exactly a fandom, but.
Okay, well, what historical figure would you love to, have a beer with, or, cook a burger with on a Friday afternoon after work and just pick their brain? Who's on that list
Yeah.
for you?
To me, someone that is incredibly interesting, but it's probably not entirely related to science at all, is John Brown. And probably people have seen this TV series that's on HBO right now. But I mean, that guy was really a maniac, and I feel like maybe I can make this relevant to science. So I feel
No,
like,
you don't have to. I mean,
yeah.
that's your answer. Go with it. You don't have to justify it.
Okay, well, so what I like about reading about people like that is that I think his worldview must have been so completely different from anything that I think about on a regular basis that I'd really just like to learn more about that. For people don't know, he was a famous abolitionist, but he was really a maniac. I mean, he was a total maniac. So I would like to know more about what was motivating him and how he thought about the world.
Okay. We've asked, I think we only asked 2 researchers this question, and we had some very definitive answers. So I feel compelled to ask you this question, Dr.
Okay.
Baumbach. Is cereal a soup?
No way. How is it a soup? I can't see it as a soup. I'm sorry. I've heard this one before. It's not a soup.
It's a bowl. It's liquid. You use a spoon.
I know. But I don't eat soup for breakfast.
This is interesting.
Could.
The physicists have strongly come down on the side of not a soup.
Really?
And so,
Not the chemist.
we asked
Not the chemist, though.
One of your
Wow.
colleagues at Los Alamos was right there with you, Ryan. It is definitively not the soup. So
Yeah.
I love
I
that.
think the context matters.
Love it. Love it.
And soups are savory. All right. That's a good point, Carrie. Savory. Yeah. Mhm.
Excellent. Excellent. Some saves coming in from the chats for you. I love it. I love it. What else do we have for Ryan?
Yeah,
if
nobody's had a sweet soup.
If you were sorted into a Harry Potter house, do you know what Hogwarts house you belong to and why?
Yeah, I not Gryffindor, the other one, the smart kids one.
Ravenclaw.
Ravenclaw. Join the club. We'll get you a scarf.
Yeah.
More importantly, what house would your crystals go into?
Ooh. I don't know. It depends on which one it is. I'll tell you what, actually, here we go. A lot of them would go into Hufflepuff. And the reason for that is that it's something like this. When you grow crystals, only about 1 in 10 of those batches actually turn out the way that you expected, okay? And then of those 10%, only 1 in 10 of them actually turn out to be something that is like really game changing, like really revolutionary. And so most of them are just good, friendly, things that, you can sort of look at and learn about, and they're kind of your friends, right? So that's why they would mostly be in Hufflepuff.
I love that. I love that. Ryan, I'm curious, you look at elements on the periodic table and think about how to mix them up and cook up some entirely new thing. Are you a good chef? Can you look at ingredients in the world the same way?
No, I cook on Saturdays and Sundays at my house, and sometimes it turns out good and sometimes it turns out not good.
And that was very definitive and confident.
I am not a good chef. No.
I love that. Is there you mentioned science fiction. Is there a mythical creature in a science fiction universe that you wish actually existed?
Well, I just read some books, can't remember the author's name, but it's called the Gateway Saga or the Gateway series or something. And it's kind of an older series. And the premise is that there's these aliens that used to occupy our solar system and other parts, but they've kind of gone missing, but they left behind their technology. And the humans find them, and then these ships, like, you press the button and the ship just takes you somewhere. And sometimes it's a black hole, but sometimes it's another great trove of artifacts. So the people are going to these different places. And those aliens are called Hichi. I don't know why they're called Hichi, but it's really fun. I like that a lot.
Okay, so you'd like those mythical aliens to exist?
Yeah, yeah. I would. They are, well, they're more like, in the end, they don't. What's good about this is they don't actually tell you what they look like for most of the thing, but then in the end, they turn out to be sort of like little burrowing creatures that live underground.
Back to Hufflepuff again, huh?
Yeah, and so it's pretty cool. But the reason I'd like it, like, I don't really care about the creatures, but if there were alien artifacts for us to go out and, get a hold of, and then, go adventuring around the solar system,
a new mystery.
That would be pretty cool.
Yeah, that sounds pretty cool. Is there anything that is invisible that you wish could be seen?
Yeah, so many things. I mean, we talk about electrons, and we want to get electrons to do things that are different from regular metals. And there must be a spatial component. There is a spatial component to that. And wouldn't it be nice to be able to just look at it and be like, oh yeah, those ones are superconductors and those ones are magnets and That would be just great.
But wouldn't that be a little less fun for you?
Well, maybe it'd look really cool. I don't know.
Yeah,
I disagree. I think with all that new information, more questions are going to come out of that. So
yeah,
probably
that's true. Yeah.
Probably true, Carlos. And then we'll spend our time on other things. Carlos, do you have any final questions?
Oh, go ahead.
We didn't ask the hot dog question. Ryan, in your world, by your definition, is a hot dog a sandwich?
Oh, no. No, I can't go with sandwich either.
Okay, so then it's a taco.
I don't think it's a taco either. That's crazy. A hot dog is a hot dog.
I love it. I love it.
You're all crazy.
I love it. I love it. This has been so much fun, Ryan, this conversation about the periodic table and all these elements. I feel like there's like 5,000 other questions we could just continue to ask you, but I think I have a hard stop at 5 because you are a dad.
That's true. I got kids to pick up.
Exactly. Ryan has to go do his other job.
That's right.
Which is being an awesome dad. But I appreciate all of you who joined us for today's Scientist Feed session. Special thank you to Dr. Ryan Baumbach for sharing his research and his, sense of being a scientist with us today. Stick around after the webinar ends. There'll be a short survey. Let us know what you thought about this session. And, go to the Open House webpage. There's more videos and, stuff to look at, games to play. We're almost through to the last day of the scavenger hunt. If you haven't tried that, try to complete the scavenger hunt to win a MagLab shrunken quarter. So you don't want to miss that.
I'm never going to get one.
Look, let me show the audience. I'm lucky enough to actually have one, if I can range it correctly. I know,
Ryan,
it's not fair.
Longer my favorite.
It's not fair. I know. You know how I got it? I got it from Scott Riggs when he left.
Oh, that's sweet.
How did Scott get one? Oh.
I don't know. And I don't know why he gave it up either. But
I'm telling you, audience, these are coveted shrunken quarters. They are made from the shrunken quarter machine. You can watch a video about how that happens on our YouTube channel too. And all you have to do is complete our website scavenger hunt. For some of you, it won't be that hard. So go give it a try. And thank you everyone for joining us at MagLab Virtual Open House. We'll see you at a future session sometime soon.
Special thanks, Kristen. Thank you for inviting me to go along on this wild, crazy ride for Virtual Open House. I've enjoyed it, and we'll see everybody soon.
Take
Bye,
care.
everyone. This was fun.